Hello, this is Chieh from Northeastern University. This is part 6 of the lecture on spectral clustering. So, in the previous video, I think we went over k-means, and k-means is a very, very popular and useful approach to cluster data based on their similarity. The closer they are, the more likely they're going to get clustered together. However, as we have seen that k-means doesn't always give you the best results. Like over here, for example, we used k-means, and yes, it used that rule where if it's closer, then it tends to cluster them together. However, that's not what we want always. Sometimes the relationship is not always proximity, but maybe some kind of geometrical relationship. So spectral clustering has the ability to find that out. Notice how it's separated the two clusters over here. And this is a really, really good approach. So today we have gone through like, I don't know, 5 videos or more than that of preparation. Today we're finally moving into the basics ideas of spectral clustering. I think is since there's a lot to digest, it's better to try to understand it step by step. And today we're going to basically go over the terminologies and the basics ideas of spectral clustering. And I think in the next video, we can then start talking about more specific mathematical derivations. So to start, we want to talk about this thing called a similarity graph. Well, the different ways to represent data. What we are used to very often is just like a table format. We have x and y, and we have the x, y, x, y, x, y. Another way is in the graph format. Specifically, like if you're talking about similarity graphs. And the way it works is, notice we have point 1 here, point 2, point 3. For each data set, we see it as a vertex in space. So V1 is this point here, V2 here, V3, V4, V5. If we get 5 data sets, we can put them in space and then connect them by edges. E1, E2, E3, E4, E5. And these edges essentially give you the relationship between them. If the relationship between V1 and V2 is high, then you get a large number. And over here, you notice V1 and V5 doesn't really have any relationship. There are no edges. So V1, V5, you want something that's low, maybe even 0, implying no relationship. And this graph is denoted with G for graph, and it contains a set of V and E. So V is vertex and E is edge. So notice there's a set of vertices. So you have this is the entire set of V1, V2, V3, basically every single vertex in this whole graph. And as well as the edges, E for edge between them. Okay, so that's what that is. And we can summarize this entire graph using this thing called adjacency matrix, which we denote as capital W. Okay, this is a convenient way to organize the data, which essentially gives a number, a weight for every single possible connection. So for every vertex, its relationship with every other vertex is organized into this entire matrix or table called adjacency matrix, and it's denoted as W. Essentially, it is the weight of each edge. If an edge is if two things are similar, they have a very high edge, implying that the connection between them is strong. And if the two nodes doesn't have one or have a very faint connection, it means that connection, their weight is small. So let's look at V1, right? So over here we have V1. If it's V1, V1, that's very close because your relationship with yourself is essentially as high as it gets. So let's give it a big number. We'll give it 5. And then V1, V2, which is here, well, it can't be 5. It's what makes sense is something that's still pretty high but smaller. Similarly, V1, V3, we'll give it a 4. But V1, V4, we want something small. And notice there are no edges connection between them. So we'll just make that 0. Similarly, V1, V5. And that's the idea of this adjacency matrix. It's a table that essentially describes relationships from one point to every other point. Now, notice that this is symmetrical. So this is 4, this is 4. Look at that's also symmetrical. That's symmetrical. So it's symmetrical. Well, it makes sense because W45 is the same as W54. Oh, by the way, I think I forgot to mention this. So W, capital W, is the entire thing, like this entire thing. But little w is one single element inside it, and is denoted by ij, where I is the row and j is the column. So this one right here, for example, is W45 because it's 4 and 5. You see? And this one right here, like this one right here is 5, 1, like that, because it's 5 and 1. That's how this notation, what this notation means. These are just important things you gotta get through, so we can basically have same vocabulary for communication. Next, we need to define this thing called degree of vertex, di. Now, di, if you look at this table again, if it's d1, we essentially, it's the relationship of one vertex with relationship to all of them, and you sum them up. So d1 is the summation of the first row. d2 is the sum of the second row, which it looks like 8 plus 5. And d3, as you can see, is w31, which is this, w32, w33, w34, w35, the summation of all these. So when you see lowercase d, you got to check out this thing here. That tells you which row we're talking about. Next, that was degree of a vertex. But what about degree matrix, the whole matrix? Well, it looks like this here. It's a whole matrix where the diagonal elements are D1, D2, D3, D4, which we got from here. Okay? Now, so that's degree matrix, and denoted with capital D. You need to distinguish the lowercase d and the uppercase capital D. Now, let's define A as a subset of V. So what was V? V is a set of, right here, V is a set of every single vertices in a graph. Now, A is a subset of that. So when you say subset, is not the whole set, is a part of the set. So right here, part of the set. And the notation for subset is this right here. A is a subset of V. That's what that says over there. Now, I also want to introduce the notation of not, this bar right here. This means not A. So if A is 1, 2, 3, A bar is 4, 5. See, essentially there is whatever is not A is in here, such that if we have A combined with not A, it gets the V back. See, if you have A and not A, it gets back the V. And that makes a lot of sense. Now, if you have A right here, A, you can also, instead of getting only A, the vertices, you can get the index. So that means if we do I element of A, instead of getting the vertices, set of vertices, we got just index 1, 2, 3. Notice there's 1, 2, 3 here. And if we do J is an element of not A, we got 4, 5. Say 4, 5. So you want to make this distinction between a subset of V and then I with index, which belongs to element A. So just indices 1, 2, 3. Now, all these just it's basically all this background information you need to know so that we have notations and you know what we're talking about. I'll do an example. Like this notation here means this. Like, why don't you pause the video and see if that makes sense to you? Okay, well, this notation here, what that means is you want to sum all the i's and all the j's not in all the i's in A, all the j's not in A. Okay, so what is that? Well, all the i's in A, as you see, here's 1, 2, 3, and all the j's not in A is 4, 5. So the combinations of that is 1. I'll write this out. W 1 4, W 1 5, W 2 4, W 2 5, W 3 4, W 3 5. So we want to sum all of them together. Now, 1 4 we already see 1 and oops, 1 and 4, that's 0. Well, 1 5 is also 0. 1 5, that's also 0. 2 4, that's also 0. 2 5, also 0. 3 4, that's not 0, that's E4. And 3 4, 3 5, 5, sorry. 3 5, that's also 0. So this notation here says that if you have two different sets, what is the connection in between the two sets? The summation of all the connections. So if you're trying to separate these two sets out, we want the connection to be as low as possible. That way it's very clear that they're two completely separate entities. So this is something we want as small as possible. Now that we've gone through a lot of the vocabulary, how do we go about finding this degree matrix? Not degree matrix, sorry, adjacency matrix. Right here, adjacency matrix, which essentially tells you the weights of each vertex. How do we go about finding that? Well, there are various ways, and depending on your research, you might want to do a one way versus another way. The one way that we actually just did is we just make it up based on what makes sense. Maybe you're an expert in the subject and you will say, well, I looked at the first piece of data and the second piece of data, and I say that the relationship is worth 7, whatever measurement you're using. And then you use the first one and then the third one, you say, okay, their relationship is also 7. And 3, 1 versus 4 is 0, 1 versus 5 is 0. You can just, based on your domain knowledge, make up this whole table. Which, if you're a domain expert, it makes sense. You look at data one by one. But this, depending on how many data you have, could take a long time. So, you gotta maybe do this at a smaller size But the second approach is you pick some distance, epsilon. And if it's within this distance, then you just say the relationship is 1 or 0. So right here, let's say that this is within the same distance, right? So you say, okay, V1 is within the same distance. We'll give it 1. V1, V2, 3. So all these equals to 1. And then obviously V4, V5 is too far away. So we'll just give all these zeros. But within 4 and 5, 4, 5, 4, 5, they are still close to each other. So we give them 1s. And that's it. This is also a pretty simple approach, except you need to pick this correctly. If imagine you pick this too big, then everything is going to be 1. Or if you pick this way too small, maybe way too small, then this would not be included. So how do you pick this? Then it gets into some questionable regions. But that's the second approach. There's a third approach called K nearest neighbor, but I don't like that approach, so I'm not going to talk about it. You can look that up, or maybe if I feel like it later, I'll teach it. But I'm going to go over the Gaussian kernel approach, which is actually probably the most popular approach. There are many different kind of kernel. And the Gaussian kernel is probably the most popular kernel. And what that says is that Wij, every single one of them, can be defined using this relationship. That is, you pick point xi and then point xj, subtract them, and follow this formula. I'll give you a quick example. Let's say vertex 3 is 2, 1, vertex 4 is 1, 1, 1, 0. So it'll be 2, 1 minus 1, 0. And then square of that. And if you do this out, it's 1, 1. You get 1, 1. And you do the magnitude, which becomes 1 square plus 1 square. You square that, which is 2. And finally, you get this. So finding this distance requires you to set this sigma value as well, which I say you can just play around this value. There are many papers written on how to actually do this, but I would say for now, let's ignore this problem. And if you were to be actually doing spectral clustering, set it up and then play around with just like set various values, and there will be one that makes sense. Okay, so these are the different kernels, and these are the various vocabularies we have gone over. Spectral clustering related to graph, and now that we understand graph can be represented this way with essentially vertices and edges, and together we can summarize this information in this thing called adjacency matrix. Adjacency matrix here. And this adjacency matrix is symmetric. So W equals to W transpose. And then we went over the degree of vertex, di, which essentially D3 gives you the sum of the third row of the W matrix. D5 gives you the sum of the fifth row. Now, degree matrix, on the other hand, is the diagonal of all the degree vertices. We have also defined a set A, which V is the whole set, all of them, and a subset of that, which is, maybe I should just delete this. Yeah. Subset of this right here. All these notations, you actually need to know it really well in order for us to move on. So I think it's a good idea to stop here so that you can have basically go over this video many times. The more times you go over, the easier it is for the next, when you watch the next video, because then we're going to move into the mathematical components of like showing how and why things work. So, all right, well, Thanks. I guess I'll see you in the next video.